All right, hi everybody. Today we're going to be looking at simple linear regression. This is going to be the beginning of our kind of dive into regression as a general topic. So simple linear regression starts at fairly simple, and we'll see we'll talk about things like correlation and look at how we visualize bivariate data with scatter plots and all that sort of thing. So the main idea is that you have some quantitative variable, some numerical variable, we call it response variable, and then we have, in general, we'd have a set of predictor variables. And the predictor variables might be, they might be quantitative, they might be categorical. So we'll look at both cases. And so we are going to be using linear regression when there is a linear relationship between the two variables. Now, what that means, that's not something that we'll talk about what that means for categorical predictors later, but for quantitative predictor variables, the idea is that you have an X variable, that's what we call a predictor, and your Y variable, which is your response. And so if you were to graph out a scatter plot, the dots would be in the shape of a line. It shouldn't look like a curve. And it'll have variation, but it will be pretty straight. And that's what you call linear relation, or linear relationship. So simple linear regression, which is what we're talking about here, is when you have just a single predictor X and a single response Y. Now, sometimes we call the predictor the independent variable, and sometimes we call the response the dependent variable. Now, the response variable, let's see. So the general statistical, the model for a simple linear regression is like the slope-intercept form of a line, which you looked at in algebra. So we're going to use B0 or B0 subscript 0. So we're going to use B0 to represent our estimate for the intercept, and then B1 as the as the estimate for the slope. So the equation is going to be y equals B0 plus B1x. Now, if you were to extend this idea to multiple linear regression, where you have multiple predictor variables, in this case, P of them, so P could be, 6 or 7 or whatever, however many, then you would basically just have one coefficient for each of them. That's going to model how much of a change you expect to have in Y when you have a 1 unit change in that particular predictor. Okay, so we'll look at scatter plots are a great tool for just examining the relation between two quantitative variables. So we'll kind of talk a little bit about that. The main thing, okay, let's look at this example and then we'll talk about what the scattered plot looks like. The PREVEND study looked at how the relationship between age and cognitive function. So as adults age, cognitive function changes over time, largely due to various cerebrovascular and neurodegenerative changes. The Prevention of Renal and Vascular End-Stage Disease, PREVEND study, measured various clinical and demographic data for participants in a series of surveys between 1997 and 2006. The data from the 4,095 participants are in the package. We'll be looking at that in lab. And so we'll be looking at the scores for the fluency test, this cognitive test ranging from 0 to 175, and a random sample of 500 from this 4,000 individual data set. So looking at the relationship between age and their cognitive score from 0 to 175. So here is a scatter plot. So what we're doing, we're going to put the predictor variable, age, as the horizontal variable, and you have your response variable, or here it's the cognitive score, as your y variable, the vertical. And this is typical. You want to have the variable that that is used to predict needs to be in the X. So you got to think about how does if there's a causal relationship, what direction does it go in? Does a person's age have an effect on their cognitive ability, or does the cognitive ability have an effect on their age? Like if somebody scores better on their cognitive test, does that make them get younger? That doesn't make any sense. But if they get older, does that make sense that they maybe are going to get worse in their cognitive score, right? So you have to think, what direction is the relation, and then the one that has the influence on the other variable, that needs to be your horizontal variable, the predictor. Now here you can see there's a lot of variation in these scores over these ages, but there does seem to be a trend downward. And it's a little hard to pinpoint exactly how much of a trend. One of the problems is the scores don't go below 20, and so although there's variability, you have this kind of cutoff around what, like 15 or 20 or so. So so a line might be a good summary of the association between these two variables, and we're going to look at how you fit a line to a scatter plot, and what is the best fit line, and what does best really even mean. It has to do with minimizing the sum of the squared residuals. Now, we haven't even talked about residuals yet, but we want to get, basically you want the line to be close to all the points on average. And we'll have to be a little bit more precise about what we mean by that, but you want the line to pretty much follow the trend. Turns out there's going to be one best line, depending on how you define best. So, but in order to really be confident in the results of linear regression, there's some assumptions that the linear model makes. One is that there is a linear trend, so this linearity assumption. And then the next is this constant variability, which is to say that the amount of variation doesn't really change as you move horizontally. So regardless of what the X value is, there's about the same amount of variability. Then there's also independence, that the values of one pair has no influence on the next person observed. And so this is something that is often violated when you have time series data, and so linear regression really isn't the most appropriate method for analyzing time series data. We'll talk more about that later, perhaps. And then the idea is that your residuals, the variation around the line, is approximately normally distributed. And so we'll look at how you evaluate each of these assumptions in due course. So what is least squares regression? So the idea, first we have to kind of define what we mean by a residual. And so when we come up with our model is going to be our predictive model is going to be the estimate for the y value based on the input value of x. So the predictor model is going to be y hat. So we used hat before for proportions, sample proportion. So the hat is an estimate. Our estimate of y is equal to b0, the intercept, plus b1 times x, right? Now, this estimate is not going to be exactly the same as what we've observed. So if for example, you in the data, you do some regression analysis. You come up with a estimate for B0 and B1. So you fit a line to the data, right? Then for every particular pair XY in your data set, you can see, well, what would have been the predicted value of Y for that predictor value X. So you can look at the difference between what the actual value Y was and the predicted value based on this model. The difference is what's called a residual. Or kind of informally call them errors. So we give them the notation E. So the E values are the residuals. So you can see here the idea that if this first data point at 40 x, you can see that we had a value of about 125 or so. But what this line that fits the data would have predicted roughly 87 or something like that. So that difference, what was actually observed minus what was predicted, that's the residual for that particular data point. So for each of these data points, you take the actual value and then you go straight down to the line and see what's the y value at that point in the line. That difference is the residual. If the data point lies above the line of best fit, it's going to be a positive residual, and if it's below the line of best fit, it's a negative residual, like this little triangle marked one toward the end. So the least squares regression line, the one we call the best, is the one that minimizes the sum of the squared residuals. So if you can imagine all the different lines that you could fit to the data, you could calculate all of the residuals for all the points. You square all those residuals and add them all up. We're trying to minimize the sum of the squared residuals. It turns out that only one particular line is going to do that. Now, we don't have to do trial and error to get that. There are automatic ways of getting those, but that's the theory behind this. Okay, now we kind of jumped straight from the idea of a linear relation to the linear model estimate, but the idea is that we're trying to estimate an actual relation that exists in real life. And just as before, where we talked about, we used mu as the Greek letter symbolizing the population mean, we're going to use Greek letters to represent the population parameters in a linear relationship. Now, so we have like the y equals beta 0 plus beta 1x plus this epsilon. Now, the beta 0 and the beta 1, those are like the true parameters that define this linear relation. And this last little term, this epsilon, is a random amount of variability. So it represents a normally distributed random variable with a mean of 0 and some constant variance or constant standard deviation. So it's like a you could think of it this way: the linear model that we're proposing to show the relation between this one predictor variable and this response is a very simple model. We're leaving out a lot of other factors that could have influence into the value of y. And all of the other variables that could influence it are going to account for a lot of variability. For one particular value x, like if it was like, in the previous one, in this example of the cognitive scores, somebody who was 55 years old, if you took all the 55-year-olds, you would have great amount of variability with their cognitive scores, right? That variability we use a normal random variable to model that variability. That's this epsilon error term. So now because it has an expected value of 0, its mean is 0. The expected value of y given some input value x is going to, we're going to drop off the epsilon term because the expected value of this distribution is always 0. So this is what we're trying to estimate: the expected value, the average y value for a given input x value. Now, there are formulas to calculate these input these coefficients. We call them B0 and B1. They can be calculated based on the correlation between x and y variables and their standard deviations and the sample means. These are the formulas for it, which we're going to look at using in the lab, but also you can use, there's a function in R that will just do the linear regression and give you the coefficients, this B0 and the B1. And this is the LM function in R. We'll do that. So we'll do this in lab, but so it's LM and then parentheses, you give the y variable and then you give a squiggle and you put your x variable. And to just get the coefficients, you add on this $ coef, which will just return the two coefficients, the intercept coefficient and the coefficient of the age variable. And you can write it out using this notation where we have the RFFT, the score, this with a hat over it. This is the estimate. Our estimated RFFT score is 137.55 minus 1.26 times the age of the person. Now, so checking the assumptions. Remember, the assumptions of linear regression were linearity, constant variability, independent observations, and approximate normality of residuals. A lot of the residual plot can give you a lot of this and can be used to check a lot of these assumptions. And a residual plot really is you just take all of your residuals and you create a scatter plot of the residuals as your the residual value, and you use your x value as your horizontal. You could also do a residual plot where you have you could have the y, the actual value y on the horizontal instead of the x value. It's going to look pretty much the same for a simple linear regression, but for multiple linear regression, because you have lots of different x values, we may need to look at different values to put on the x axis. So yeah, as far as independence go, you have to think about how the study was constructed. For linearity, for constant variability, and approximate normality, you can use the residual plot, and you can use like a QQ plot. So you can like do a QQ plot for the residuals, as we've done before. You can see if the residuals fall along the diagonal on a QQ plot. You could also just look at a histogram of residuals to see if it follows a somewhat normal distribution as well. So here we have an example of a scatter plot, x and y, just generic variables, no information about them. What we have, you can see the red line shows the linear model, and then you have all of the dots with variation around them. If we look at instead of plotting the y value, we plot the residual, you get a residual plot. So you can see on the graph on the right, all of these dots all over the place, these are the residuals that correspond. So actually what's happened is we've taken this slanty line, we've straightened it out, and then it kind of becomes scaled up. So now the residual plot always has a mean of 0. The residuals always are on average 0. So you're going to have variation around 0. What you want to look for is you want the amount of spread from the 0 line to be about the same no matter where you are horizontally. This looks pretty good. This looks like constant variability. Here's an example where linearity is violated. You can see that in the scatter plot, that the residuals are tend to be above the line at the beginning and the end of the x values, and actually this is labeled incorrectly. It should be residual plot of y versus predicted value, which is going to look the same pretty much as versus x. But you can see that there's this curve to it. So one thing you don't have, it looks like I don't know if the variability might be about the same over it, but it definitely does not satisfy linearity. If you don't have linearity, there are things you can do to get around that, which we'll talk about later. But you shouldn't just be satisfied with your linear model if you are obviously violating linearity, because you could actually do a better fit. So let's see. Yeah, checking the normality. So we talked about this a little already. If you take you can do like a QQ plot, or you can look at the histogram of the residuals to check normality. Now, interpreting linear model. We have, I guess, one possibility is to look at if you have predictor variables that are categorical, how you would how you would use linear regression in that case. So if you have a categorical variable with more than, so if we have more than one level for our categorical variable, we have to be be clever about how we do things. But what we're going to do, oh yeah, that's true. With simple linear regression, you can only have two levels for your categorical variable. There's not much more complicated, but we'd have to use multiple regression if you have three or more levels. When I say levels, it's like values. So if, for example, our categorical variable would be something like man, like the person's sex, man or male or female, something, if we simplify it like that, then you've got only two levels, two values that the categorical variable can take. So here we'll look at what we do with that. Remember, we looked at this before. The arm strength, the non-dominant arm strength change after these exercises that both male and female participants encountered, what we would, so here we're looking at, we would try to be predicting a person's percentage change in arm strength based on whether they're male or female. So let's see. Right. So first, what you see here is it's just we're calculating the average percentage change in arm strength for the men, females versus males. Right. You can see it was on average 62.9272% for females, 39.23512% for males on average. So when you fit a linear model to the percentage change arm strength with sex as the only predictor, the intercept is 62.92, and then the slope coefficient, which is the coefficient for whether the person's male or not, is going to be the difference in the two percentage changes. So what happens is, basically you take your data and you encode female as 0 and male as 1. It just assigns it alphabetically. The first one gets encoded as a 0, and so then the linear model is going to be pretty simple. It's just going to be you predict 62.93 if they're female, and if they're male, you subtract the difference so that the resulting prediction is going to be 39.23512. Now this is very simple, but this is going to be extended to when we do multiple regression. You can have categorical variables, and then you can have multiple levels of them as well. So we've talked about correlation before. The correlation coefficient is a measure of how strong a linear relation is between two variables. And the correlation coefficient, or Pearson's correlation coefficient, ranges from -1 to 1. For a linear regression, we tend to use r squared, which is, for a simple linear regression, literally we take r, the correlation, and we square it. But for a more complicated regression, r squared isn't quite so simple to calculate. Now, as I said, it is actually the correlation squared, but it also can be interpreted as a ratio of variation. So if you look at the amount of the variance of the predicted values, and then divide that variance by the variance of the observed values. So this is to say, if you just took what you're going to get is what proportion of the variation in the y variable, what proportion of that variation is explained by our linear model. So if the r squared came out to be 0.739, you'd say 73.9% of the variation in the cognitive score is explained only by age. The higher r squared is, the better your linear model does to explain your response variable. It can be as low as 0 or as high as 1. That's the range for r squared. You can calculate it a couple different ways. In fact, so the variance of the residuals plus the variance of the predicted values equals the total variance. And actually, we'll look later on this idea of sum of the sums of squares and all that when we look at an ANOVA table. So actually, ANOVA is you can use ANOVA to look at how well your linear model fits the data. So anyway, we'll be looking at this in lab. Okay, let's talk about the idea of outliers. So data points in a scatter plot have varying degrees of contribution to the estimated coefficients. Typically, the more of an outlier some data point is, and particularly when the x value is really high or really low, it's said to have very high leverage and a big effect on B0 and B1. So the further this data point is from the average y and from the average x, that's going to have a big effect on its leverage. A data point's called a regression outlier if its value for the response really doesn't follow the general linear trend. So where its residual is way far off. Maybe its residual is like greater, because residuals are standardized. Actually, they're not. So if the residual is like has a z-score of if you did standardized residuals, if it had a z-score of like 4 or more, or like more than 4 or less than -4, that would be very extreme. Even 3 would be pretty high. So when a data point has a big effect on the regression model, if it has high leverage or if it's an outlier, and if you omit it, it has a big change. It's called an influential observation. And usually outliers with high leverage are influential. I guess not always, but oftentimes they are. So let's see. We'll look at a scatter plot of infant mortality versus the number of doctors, where the observations are for each state and for the District of Columbia. So we have 50 states where we're looking at the number of doctors in that state and the infant mortality. That's per 1,000 and number of doctors per 100,000. So you can see that you have this in green. In red, you have the line that fits all 51 observations. But there's this one point you can see where there's 800 doctors for every 100,000 members of the population, and you also have really high infant mortality rate. But if you exclude that one point, that's very high leverage because it's very far away from the average x value, and it's also very far away from the regression line. Its residual is very high, and you can see when that is removed from the data set, we only fit a model to the 50 observations. We get a very different shaped line. It's sloping downward instead of upward, and that's what you would expect to see, where as the number of doctors increases, you have a lower infant mortality rate. So the point marked in red is the District of Columbia, where there was approximately 800 doctors per 100,000 members of the population, and the infant mortality rate was 11.3 per 100,000 live births. So yeah, because you have it's very high leverage. 800 is very high value for the predictor, and you have the residual being very, very high also, and it's extremely influential. The line is very different when that's removed. Okay, so we'll look at some of the types of statistical inference that we can do with regression. Because we're trying to estimate beta 0 and beta 1 using our linear model, B0 and B1, these estimates are, one question we want to ask is there enough evidence from the data to really justify using a linear model? If there's no true relationship between the x variable and the y variable, then this slope coefficient, this beta 1, in reality is 0. And so what we're going to ask is there enough evidence from the data to conclude that this slope is not 0? And this is how we would set this up in a hypothesis test. So the null hypothesis would be that there's no true association between the variables, that beta 1 equals 0. And the alternative hypothesis is that beta 1 is not 0. So it's either positive or negative, but it's not 0. We calculate a t statistic, and it's going to have n minus 2 degrees of freedom. We're going to, it's going to be calculated by B1 over the standard error of B1. Now, the standard error of B1, it's a little complicated to talk about here, but it's calculated for you by the software. And so, yeah, you take the slope coefficient estimate, divide it by its standard error, which, again, I'm not going to tell you how to calculate. And that's going to give you a t statistic. And then you can see how extreme that t statistic is. You can also calculate a 95% confidence interval for the slope by taking that slope coefficient estimate and adding and subtracting a margin of error using the same formula we've used before. And like I said, the standard error, there's formulas for calculating standard errors, but in practice, you're not going to want to do those by hand. And that covers it for simple linear regression. There's a lot of new concepts, and we want to master these before we move on to multiple linear regression. And that's when things get really fun. All right, I'll see you in class. Bye.